Honorable guests, distinguished speakers, and esteemed delegates, today we gather on this esteemed platform to delve into the realms of possibility and envision a future where the convergence of artificial intelligence and robotics reshapes the landscape of healthcare delivery.
Me, Kannan Mahalingam, and Sreekanth Pallavoor, Dr. George Ghosh is a gem of a person and professor of head of the Department of Cardiology. These are the people attending.
Thank you so much, sir. Let's now delve into the next segment of the conclave, technical session. I am pleased to welcome visionary leaders in technology to the stage. Mr. Sreekanth Pallavoor and Ms. Amritha Pallavoor, the founders of CARAIO Technologies. Mr. Pallavoor's visionary leadership has significantly shaped CARAIO Technologies, while Ms. Amritha's expertise in AI, machine learning, computer vision, and image processing is showcased through her current role as an AI intern at Intel Corporation, Bangalore. Today, Mr. Pallavoor and Ms. Pallavoor will delve into the realm of artificial intelligence and cytogenetics, unraveling the profound intersection of technology and genetics. Please join me in warmly welcoming them.
It can lead to fatigue when it's done over a long period of time, so this is a drop in accuracy. And because of all of these issues, eventually efficiency is also a major problem that needs to be addressed. So can we solve these problems using technology, which is what we are trying to do at CARAIO Tech?
So touching a bit deeper on the problems, as Amritha told, mostly this is concentrated in major cities. In Kerala, I understand cytogenetics clinics are very less, right? Mostly Kochi, Trivandrum, only these two. In Bangalore, I live in Bangalore. So in Bangalore, there are a few handful. But if you go to the suburbs or to the villages, nothing, right? So accessibility is a problem. Affordability, the test cost is very high, right? 3,000 to 15,000 rupees is a lot of money. It's not a common man can afford, right? It may majority of the population, which is below the which is on the lower side of the pyramid, I would say, right? Economy-wise, they cannot afford this. And training and skill set, like what Amritha told, the training problems are, currently there are trainings happening. For example, Dr. Rai himself tells me, the way training is happening is it has not penetrated, it has not leveraged the digital. Now digital is getting into everywhere, right? So digital penetration has not happened into the training. That is one thing. And of course, wet lab dependency is there. So if you make it digital, we can decouple it from the wet lab dependency, right? And then the efficiency and accuracy, every manual image analysis takes about 10 to 20 minutes of time to analyze the metaphase image to produce a karyotype. And for one reporting of one patient, we need close to 30 images. And in US, I heard it is about 50 images. So in a day, what we are talking is you can only turn around, say, 3 cases of reporting in a day, in an 8-hour working window, right? It is not at all efficient. In addition to that, the images have got touching and clustered chromosomes coming in, which is very difficult for even for experienced doctors to handle that. So all these are complexities which we have studied, and then with the guidance of Dr. Roy and other cytogeneticians, we have studied, and as engineers, we are trying to solve this, right? So that's where the solution is coming. Our product is more of a platform. Rather than calling it a product, it's an AI platform. So it's an artificial intelligence cloud-enabled platform, which, what we have made is, there are products existing today. For example, Dr. Roy's kind of clinic is using a product, of course, but those products are costly. And number two, they are all made out of India. The leading players are in Europe or Israel or America. Only these 3 regions. No Indians have got into this, right? So what we are trying to develop is more of a hardware agnostic karyotyping. See, there is a hardware part existing into that will remain the same. The wet lab process will remain the same, but if you capture digital image, you can put it into a cloud and then AI will do the job. Like what we saw in the other cases of, right, whatever the other teams also show. Once you digitize the data, it is easy to put it in the cloud and make AI do the job. That's what we are trying to do. Automated decision making happens. Easier to train and learn. So, and then telemedicine enabled. Right from morning, we have talked about telemedicine. So this is about enabling telemedicine for cytogenetics. That's what we are trying to, which doesn't exist today. Amritha can talk more about the AI details.
So this diagram here gives us an overview of how this works end-to-end. We have a layer here, which is AI models are exposed as services, and it operates in a cloud platform. And this can be abstracted into two types of applications. On the left hand, we have the lab training application, mainly for education, and also the diagnostics lab application, which is for telemedicine enablement. And this works for decision-making scenarios. Getting a closer look into how this works. So this is an end-to-end flow where we give an input metaphase image, and it gets processed by the AI models and produces an output of a karyotype image. So what's happening internally is first when you get an input metaphase image, the chromosomes here are scattered, and the model itself segments these individual chromosomes and gives you about 46 individual chromosome images, which is the typical number of chromosomes in any human being. And now these chromosomes are analyzed by the models, which have already been pre-trained, to classify these chromosomes into one of the 23 types of chromosomes. So we tried a lot of deep learning models and also tried an ensemble of many deep learning models. Some of them is, to mention, SqueezeNet is one model that we tried. So these models do the prediction of classifying the chromosome and producing the end-to-end final karyotype image, which is a replica done by an automation procedure.
So that output which you saw is created by our core AI engine, which does the job, as I told earlier. For one image analysis, it takes even an experienced doctor at least 10 minutes to 20 minutes. This does it hardly in a matter of few seconds, maybe 10 to 20 seconds. That's what it does. Like, it may not be perfect, of course, so doctors will have to do the correction. We provide the opportunity for the doctor to verify it manually, then correct it, anything, right? And we are also implementing sort of a way where AI will learn through a human feedback, and then AI will improve over the period. Like what in the morning it was told that it's not AI which is in the front, it is human, right? Yeah, of course, that's what we are trying to enable here, right? Human input is the key here, and AI is augmenting the human input to produce the expertise, right? So I think we talked about this. What this slide says is, see the current scenery, as I told, there are products from this Israeli company, of the US, European majors, big players, but they have, the underlying problem in that is they do not have training as a focus. They do not have telemedicine as a focus. They got all on-premise software, right? And then affordability is a key problem with that because they are all tied to hardware. So if you want just the software, you want to put a small clinic in the remote part of India, and then just take the samples and then collect it and do the process and push it into the cloud. And then in cloud, all the AI, like Dr. Dinesh Roy's work, it will happen in the cloud by AI, right? And Dr. Dinesh Roy sitting here can look at it and then approve it, correct it, approve it, or whatever it. That possibility will reduce the cost a lot. That 3,000 to 15,000 rupees cost will come down dramatically with that, right? And accuracy, I think I spoke about that. So briefly about our company, as I told, we started in Bangalore a couple of years back, and with the vision of making cytogenetics more efficient, accessible, and affordable. So we are incubated in University of California, Berkeley. And our market focus is US and India, this being incubated in US, and the parent organization is an American company. So, and our key collaborators, apart from UC Berkeley, Dr. Roy's institution, Genetica, they are our key collaborator. Apart from that, in Bangalore, CCAM, Center for Cellular and Molecular Platforms, which is part of TIFR, and IISc, and PS University, right? Very briefly, our team, myself and Amritha, I am an AI engineer with the management background. I studied in Haas School of Business, UC Berkeley, and Amritha is a final semester student in PS, and she has done her internship in Berkeley lab as well. Dr. Dinesh Roy, so you all know him, I do not want to introduce him, but he's key. The domain part of knowledge is coming from him, right? And the right side, you can see Dr. Sundaresan is also another cytogenetician. He's a veteran based in Bangalore. He has also helped us. Dr. Harijit is originally from Trivandrum. He is a medical professor. He is a user of karyotyping based in Case Western University, US, right? That's the team. Apart from that, we have got advisors from UC Berkeley's Skydeck Accelerator. Right? So very briefly about our product, some screenshots.
So I'll just give a quick walkthrough of how our application works. So this is the landing page where the user gets access to multiple set of lessons where they can familiarize themselves with how to classify chromosomes and understand morphology and other landmarks to identify and classify them into one of the 23 pairs. So with this knowledge, we move on to the next page. So this is the karyotype output, which has been generated from our AI model. And this serves as a ground truth that the students learn from. And this also has enablement for corrections to be done by a human expert as well. So this is the main page where all the individual extracted chromosomes keep popping up in the little box here on the right. And these chromosomes can be dragged and dropped accordingly into one of the 23 classes, which the user thinks is appropriate for that chromosome. So based on what they know, they place it accordingly into the corresponding class of chromosome. And they can also validate this by clicking on a validate button, and it gives you the number of correct and incorrect and also partially correct chromosomes that has been done so far. So if it's partially correct, in that case, it's either inverted or lateral inversion. So these corrections can be done accordingly. And a main aspect of our software is it has enabled GPT, a chat GPT feature, where we have a subject matter expert as such, which has been trained to give information about helpful hints for identifying a chromosome. So if the user is stuck, then they can ask for a helpful hint, and the chat GPT will give you on information about how to classify, say, chromosome 3 and chromosome 4 and so on.
So in fact, in today's world, more than AI, it is generative AI or Gen AI, which has become more popular with the outcome of ChatGPT in November 22, right? It's penetrating into every field, and it's about developing Copilot. Copilot is an AI thing, is an AI engine which is sitting with a human and then which is doing all the jobs, right? It's a Copilot. So what we are trying to develop through that is a Copilot built for cytogenetics. And what it needs is cytogenetics content. That's why we have got these lessons here. So these lessons are the ones from where the chat GPT will learn. We have got a lot of pages of lessons, and then it will learn. And then eventually the co-pilot through chat GPT or whatever, right? That will be the supporting entity for the doctors to use, right? So that's what it is pretty much. So from us, any questions, we'll be happy to answer. Thank you very much.
Thank you, Mr. Sreekanth Pallavoor and Ms. Amritha Pallavoor, for sharing your brilliance and vision with us.